Chapter 2, Unit 2, Population and Migration Patterns and Processes. 2.1 Population Distribution and Density. Where does everyone actually live? Let's start with a thought experiment. Imagine you're looking at Earth from space, not the beautiful blue marble photo, but a map that lights up wherever people are living. What you'd see isn't a uniform glow. You'd see blazing clusters of light in South Asia, East Asia, and Western Europe, and vast dark stretches across northern Canada, the Sahara, and Siberia. That uneven pattern of light? That's population distribution, and understanding why it looks that way is exactly what Section 2.1 is all about. Population distribution simply means the way humans are spread across Earth's surface. And here's the central truth the AP exam wants you to internalize. Population is not distributed randomly. It is driven by a combination of physical geography and human factors, and your job is to know both categories cold. The physical factors, nature sets the table. Think of physical geography as the table that humanity sits down at. Some seats are comfortable, others are nearly impossible to occupy. The most densely populated areas on Earth tend to share certain physical characteristics. They have mild climates, not too hot, not too cold, not too dry. They sit near water, whether that's rivers, coastlines, or lake systems, because water means agriculture, transportation, and trade. They have flat, fertile land, the kind of alluvial plains you find in river deltas. And they sit at low elevations, generally below 500 meters, where agriculture is easier and oxygen is plentiful. Now, flip that around. Sparse populations cluster in areas with extreme cold, think Siberia or northern Canada, extreme aridity, the Sahara, the Arabian Desert, the Australian outback, very high elevation, the Tibetan Plateau, or dense tropical rainforest parts of the Amazon basin. The AP exam loves to give you a map and ask you to identify why a region is sparsely populated, so practice running through that checklist. Climate, terrain, access to water, elevation. Here's an edge case that trips students up constantly. High elevation is not always a barrier. The Andean highlands of Bolivia and Peru and parts of Ethiopia have supported dense populations for centuries because local adaptations, agriculture suited to altitude, and cultural history made those environments workable. On an MCQ, don't just see mountain and automatically think sparse. Context matters. The human factors people build on what nature offers. Beyond physical geography, human decisions shape distribution too. Economic opportunity draws people. This is why coastal cities and capital cities tend to be densely populated even when the physical environment isn't uniquely special. Historical patterns matter enormously. Once cities form, they attract infrastructure, which attracts more people, which justifies more infrastructure. It's a self-reinforcing cycle. Political factors also play a role. Forced settlement, colonial patterns, and government policies like China's historical hukou system have all shaped where people live. The four major population clusters you absolutely must know for the AP exam are South Asia, centered on the Indo-Gangetic Plain, India, Bangladesh, Pakistan, East Asia, Eastern China, Japan, the Korean Peninsula, Western Europe, and Eastern North America. These four clusters account for the vast majority of humanity, and you should be able to locate them on a map instantly. The formula's arithmetic density is just the beginning. Now let's talk numbers, because the AP exam will absolutely ask you to calculate and interpret these. You need to know three distinct types of density, and confusing them is one of the most common traps on this exam. Arithmetic density, also called crude density, is the one most people think of when they hear population density. The formula is simple: total population divided by total land area. If a country has 100 million people and 1 million square kilometers, its arithmetic density is 100 people per square kilometer. This is useful for quick comparisons, but it has a major limitation. It treats all land as equally usable, which is almost never true. Physiological density goes deeper. It's calculated as total population divided by the amount of arable land that can actually be farmed. This gives you a much more meaningful picture of how much pressure people are putting on the land that feeds them. Egypt is a perfect example. Egypt's arithmetic density looks moderate because the country is huge, but most of Egypt is the Sahara Desert. Virtually everyone lives in the Nile River Valley and Delta. Egypt's physiological density is among the highest in the world, signaling serious agricultural pressure. When the AP exam shows you a country with a much higher physiological density than arithmetic density, that's your signal that the country has significant uninhabitable territory. Agricultural density rounds out the trio. It's the number of farmers divided by arable land. This measures agricultural efficiency. A country with a low agricultural density like the United States has very few farmers relative to its farmland, because mechanized agriculture means one farmer can work hundreds of acres. A high agricultural density, like in parts of sub-Saharan Africa or Southeast Asia, means many farmers working relatively small amounts of land, often indicating subsistence farming and lower technological development. The AP exam frequently asks you to compare these three densities for the same country and draw conclusions. Practice that skill explicitly. Reading the maps and avoiding the traps. When interpreting population distribution maps on the AP exam, watch for a few classic traps. First, don't confuse density with total population. Bangladesh has an extremely high population density but a smaller total population than Brazil, which has a much lower density. Second, don't assume that wealthy countries are always densely populated. Canada and Australia are wealthy but sparse. Third, watch for ecumene versus non-ecumene. The ecumene is the permanently inhabited portion of Earth's surface, while the non-ecumene refers to areas too harsh for permanent settlement. The AP exam has used this vocabulary directly, so know it. Connections to the rest of the course. This section doesn't live in isolation. It's the foundation everything else in Unit 2 builds on. Understanding where people are is the prerequisite for understanding why populations change, birth rates, death rates, migration, which is coming up in sections 2.2 through 2.5. Population distribution also connects to Unit 1's concept of geographic scale. A country can look uniformly dense at one scale, but show intense clustering at another. And it links forward to Unit 6 on cities, because urban geography is fundamentally about why population clusters in certain places and not others. Think of 2.1 as drawing the map on which the rest of the course places its pieces. With distribution and density firmly in your toolkit, you're ready to explore how populations change over time, and that means stepping into the fascinating world of birth rates, death rates, and the demographic transition model in Section 2.2. 2 consequences of population distribution. Why, where people live, changes everything. Let's start with a thought experiment. Imagine you're the mayor of a mid-sized city, and one morning you wake up to discover that overnight, half your population has moved to a single neighborhood on the east side of town. The west side is now a ghost town. What do? Your roads, schools, water pipes, and hospitals were all built for an evenly distributed population. Suddenly, nothing works the way it should. That's the core insight of this entire section. Population distribution isn't just a statistic. It has real cascading consequences for governments, economies, and environments. And the AP exam is going to test whether you understand exactly what those consequences are. Ecumene and non-ecumene, the foundation. Before you can understand consequences, you need the foundational vocabulary. The ecumene is the permanently inhabited portion of Earth's surface. The non-ecumene is the portion that is uninhabited or only temporarily occupied. Think Antarctica, the Sahara's deep interior, or the highest reaches of the Himalayas. Here's the first trap the AP exam sets. Students assume the ecumene is expanding uniformly. In reality, climate change and technology are pushing the ecumene into previously uninhabitable areas, but environmental degradation is simultaneously shrinking habitable zones elsewhere. Expect an FRQ that asks you to explain why a specific region might shift from non-ecumene to ecumene, and be ready to tie your answer to climate, technology, or resource extraction, not just more people exist. Population density, 3 types you must know cold. Population density is the engine that drives consequences, and the AP exam expects you to distinguish between 3 distinct types with precision. Arithmetic density is the most straightforward, total population divided by total land area. The formula is simply arithmetic density equals total population divided by total land area. If Bangladesh has roughly 170 million people and about 148,000 square kilometers, you get approximately 1,148 people per square kilometer. This is the number you see in textbooks and on demographic maps. But here's the problem. It treats every square kilometer equally, whether it's farmland, desert, or mountain. That's where the exam starts getting tricky. Physiological density is far more revealing. The formula is physiological density equals total population divided by total arable land. Arable land means land capable of being farmed. Egypt is the classic example, a country with vast territory, most of it the Sahara Desert, where nearly the entire population lives along the Nile corridor. Egypt's arithmetic density looks moderate, but its physiological density is among the highest on Earth. When the AP exam shows you a country with a low arithmetic density, but a very high physiological density, that's your signal. Agricultural pressure is intense, food security may be fragile, and land is being strained well beyond what the simple population-to-land ratio suggests. Agricultural density completes the trio. Agricultural density equals number of farmers divided by total arable land. This one measures farming efficiency. A country with a low agricultural density, meaning few farmers per unit of arable land, likely has mechanized, industrialized agriculture. Think the United States or Canada. A country with a high agricultural density has many subsistence farmers working small plots, which often signals a less developed agricultural economy. The classic MCQ trap here is assuming high agricultural density means productive agriculture. It doesn't. It typically means the opposite. More farmers on the same land usually indicates low technology and low yields per farmer. Connecting these three, when you compare all 3 density figures for a country, you can build a story. High arithmetic, high physiological, high agricultural together suggests an overpopulated, agriculturally stressed, developing nation. High arithmetic but low physiological and low agricultural suggests a highly urbanized country with efficient farming. The AP exam loves asking you to infer development level or food security from density combinations. Overpopulation, underpopulation, and carrying capacity. Here's a misconception trap that shows up constantly. Overpopulation is not simply about large numbers. Overpopulation means a region's population exceeds its carrying capacity, the maximum number of people an area can sustainably support given available resources and technology. You can have overpopulation in a country of 5 million if the resources are scarce enough. Conversely, China isn't automatically more overpopulated than Luxembourg just because it has more people. Luxembourg, with its high resource consumption, arguably places more strain per capita on global systems. This connects directly to Unit 5 agriculture and the concept of the Malthusian theory you'll encounter in Unit 2's broader themes. Thomas Malthus argued that population grows geometrically while food supply grows arithmetically, leading to inevitable resource crises. The AP exam won't ask you to take a position on Malthus, but it will ask you to apply his logic and to recognize where neo-Malthusian thinking influences contemporary population policy debates. Consequences for infrastructure, services, and the environment. When population clusters in specific areas, the consequences ripple outward in 3 major directions. You should organize your thinking around infrastructure strain, resource depletion, and political representation. Dense population clusters, particularly megacities like Tokyo, Cairo, or Lagos, create enormous pressure on infrastructure. Roads congest, water systems strain, waste management overwhelms planners, and housing costs spike. The AP exam may give you a scenario about a rapidly urbanizing city in sub-Saharan Africa or South Asia and ask you to predict consequences. Your answers should invoke infrastructure stress, informal settlements, squatter settlements, or shantytowns, and strain on government services, all consequences of rapid population redistribution, not just population growth. Sparsely populated areas face mirror image problems. Governments struggle to justify building expensive infrastructure, hospitals, highways, high-speed internet, when few people will use it. This connects to Unit 4's discussion of political geography. Areas with low population density often have less political representation, fewer services, and higher per capita costs for the services they do receive. Rural depopulation in countries like Japan or in the American Great Plains creates what geographers call a population implosion at the local level, where tax bases shrink, schools close, and communities enter a self-reinforcing cycle of decline. The critical FRQ move, connecting distribution to policy. For the FRQ, the most sophisticated move you can make is connecting population distribution consequences to specific government policies. China's hukou system, internal migration registration, was explicitly designed to control the consequences of uneven distribution. Singapore's housing policies aim to prevent ethnic clustering. France's regional development programs try to counteract the gravitational pull of Paris. When an FRQ asks you to explain how governments respond to population distribution challenges, you need specific examples with specific policy mechanisms, not vague gestures toward the government builds more stuff. Keep these 3 density formulas locked in your memory. Practice distinguishing overpopulation from high population, and always ask, what are the downstream effects of where people are and aren't? With that framework solid, you're ready to move into the patterns of population change itself, which is exactly where we're headed next as we explore fertility rates, mortality rates, and the demographic transition model. 2.3 Population composition and population pyramids. What is population composition, and why does it matter? Imagine you're a city planner trying to figure out how many elementary schools to build, how many retirement homes to fund, and how many job training centers to open all at the same time. You can't make any of those decisions just by knowing how many people live in your city. You need to know who those people are. That's exactly what population composition is about. Population composition refers to the structure of a population, broken down by characteristics like age, sex, race, ethnicity, and language. For the AP exam, you'll be expected to understand 2 characteristics above all others: age structure and sex ratio. These 2 variables, when visualized together, give us one of the most powerful analytical tools in all of human geography, the population pyramid. The population pyramid, how to read, draw, and interpret it. Think of a population pyramid as a bar graph that's been split down the middle and flipped on its side. The vertical axis in the center represents age cohorts, typically grouped in 5-year intervals, 0 to 4, 5 9, 10 to 14, and so on up through 85 and older. The horizontal axis represents the percentage, or sometimes the raw number, of the total population in each cohort. Males are always on the left side. Females are always on the right side. This is a College Board convention you must memorize. Swapping the sides is a classic FRQ mistake that can cost you points. Each horizontal bar represents one age cohort for one sex. The bars grow shorter or longer depending on how many people are in that group. When you're asked to sketch or label a population pyramid on the FRQ section, make sure you include all of this: the centered vertical axis with labeled age cohorts, the labeled male-female sides, a title, and axis labels showing percentage of population. The overall shape of the pyramid is where the real analysis begins, and the AP exam loves to test whether you can connect shape to stage of development. The 3 classic shapes and what they tell you. The first shape is the expansive pyramid, wide at the base, narrow at the top, literally shaped like a triangle. This shape tells you that a country has a very high birth rate and a high death rate. There are lots of young children at the bottom, but population thins out dramatically with age because people aren't living as long. Think of a country in stage 2 of the demographic transition model like Niger or Mali. The base is so wide it almost looks like it could tip over, which is an apt metaphor, because these countries face enormous pressure to provide for surging youth populations. On the AP exam, an expansive pyramid signals high CBR, high CDR, low life expectancy, low median age, and a population that is growing rapidly. The second shape is the constrictive pyramid, and here's where students often get confused. A constrictive pyramid is actually narrower at the base than in the middle. The bottom bars are shorter than the bars a few rungs up. This happens when birth rates have fallen significantly, so there are fewer young people entering the population than there were in previous generations. Countries like Germany, Japan, and Italy show this pattern. A constrictive pyramid signals low CBR, low CDR, high life expectancy, aging population, and potential labor shortages and pension crises down the road. The AP exam will sometimes describe a country facing challenges supporting its elderly population and ask you to identify the pyramid shape. The answer is constrictive. The third shape is the stationary pyramid, more of a column or rectangle than an actual pyramid with roughly equal-sized bars from bottom to middle and only tapering near the very top. This represents a population where birth rates and death rates are both low and relatively balanced. The United States and France are reasonable examples. Zero population growth, ZPG, is associated with this shape, and it corresponds to stage 3 or early stage 4 of the demographic transition model. Sex ratio, dependency ratio, and the numbers you need. The sex ratio is defined as the number of males per 100 females in a population. A balanced population has a sex ratio near 100. Countries like China, because of the historical one-child policy and its associated sex-selective practices, have a skewed sex ratio with significantly more males, which you can actually see in population pyramids from China, where the bars for younger cohorts bulge more on the left, on the FRQ. If you're given data about a country with a highly imbalanced sex ratio, you need to explain the cultural, historical, or migration-based reasons behind it. The dependency ratio is a formula you absolutely must know. It equals the number of dependents, people aged 0 to 14 plus people aged 65 and older, divided by the working age population, ages 15 to 64, multiplied by 100. A higher dependency ratio means more economic strain on the working population. Countries with expansive pyramids tend to have high dependency ratios because of the massive youth bulge. Countries with constrictive pyramids also face rising dependency ratios, but for the opposite reason, the elderly cohort is growing faster than the workforce. This is a classic MCQ trap. Both expansive and constrictive pyramids can produce high dependency ratios, just from different ends of the age spectrum. Common traps and connections to watch for. One of the most frequent MCQ traps is confusing life expectancy with median age. Life expectancy is the average number of years a person is expected to live from birth. Median age is the midpoint of the age distribution. Half the population is older, half is younger. A country can have increasing life expectancy while still having a low median age, as long as birth rates remain high. Don't assume these always move together. Another trap involves population momentum. The idea that a population will continue growing for decades even after fertility rates drop to replacement level, simply because there's such a large cohort of young people who haven't yet reproduced. This often appears in FRQs asking you to explain why a country's population is still growing despite recent decreases in birth rate. This topic connects powerfully to the rest of Unit 2. Population pyramids are essentially the visual representation of where a country sits on the demographic transition model, and they predict migration patterns, urbanization pressures, and economic challenges you'll study in later units. They also connect to Unit 7 when you analyze how a country's age structure shapes its industrial development and labor force needs. Understanding who lives where and at what stage of life is the foundation for almost every geographic pattern you'll analyze from here forward, which is exactly why we're about to zoom out and examine how populations move across space in our next topic on migration patterns and processes. 2.4 Reading and Interpreting Population Pyramids. What is a population pyramid? Picture a snapshot of an entire country's population frozen in time, every person sorted by age and sex, stacked up like layers of a cake. That's essentially what a population pyramid is. The College Board defines it as a double bar graph that displays the age-sex distribution of a population. On the vertical axis you have age cohorts, typically grouped in 5-year intervals, 0 to 4, 5 to 9, 10 to 14, and so on up to 85 or older at the very top. The horizontal axis shows population size or percentage of the total population. Males are conventionally plotted on the left side, females on the right. When you see this on the AP exam, remember, left is always male, right is always female. A trap question will sometimes ask you to identify which side is which, and you need to have that locked in. The reason geographers love this tool is that it compresses an enormous amount of demographic information into one elegant visual. In about 10 seconds of looking at a pyramid, you can infer a country's birth rate, death rate, life expectancy, dependency burden, and even its political and economic history. That's a powerful skill, and the AP exam absolutely tests whether you can do exactly that. The 4 classic pyramid shapes. The College Board expects you to recognize, describe, and interpret 4 fundamental shapes. Think of them as characters in a story about a country's demographic journey. The first is the expansive pyramid, which looks like, and here's your analogy, a Christmas tree. It has a very wide base and narrow top, indicating high birth rates, high death rates, and a young, rapidly growing population. This shape is characteristic of countries in stage 2 of the demographic transition model. Think of sub-Saharan African nations like Niger or Mali. The wide base tells you that many babies are being born each year, but the pyramid tapers quickly as you move up because people are not living into old age in large numbers. When you see this shape on the exam, the words that should fire in your brain are high fertility, high mortality, rapid natural increase, low development. The second shape is the constrictive pyramid, which actually narrows at the bottom like a top-heavy beehive or a coffin. This shape means birth rates have fallen so dramatically that each new generation is smaller than the one before it. You find this in stage 5 countries, or late stage 4. Think Germany, Japan, Italy, or South Korea. The critical implication here is negative natural increase, an aging population, and a shrinking labor force. The AP exam frequently asks you about the economic consequences of this shape. A country with a constrictive pyramid faces enormous pressure on its pension systems and healthcare spending because a small working-age population has to support a large elderly cohort. The third shape is the stationary pyramid, sometimes called a stable pyramid. It looks like a column or a gentle rectangle, roughly equal width from bottom to top with a slight rounding at the upper end. This reflects low birth rates balanced by low death rates, a hallmark of stage 3 and early stage 4 countries. The United States trends toward this shape, though with some variation in the middle cohorts because of the baby boom. The fourth shape isn't always given its own name, but you need to recognize irregular or distorted pyramids, those with unexpected bulges or indentations at specific age cohorts. This is where things get really interesting on the exam. Interpreting bulges, indentations, and distortions. A bulge in a pyramid is like a scar. It tells you something happened. The most famous bulge in American demographic history is the baby boom cohort, the large generation born between roughly 1946 and 1964. On a U.S. population pyramid, you'll see a wide bar in the 55 to 74 age range today. That big generation still moving through the pyramid like a pig through a python, an analogy demographers actually use. A bulge in the working age cohort, roughly ages 15 to 64, suggests strong economic productivity potential. An FRQ might show you this and ask you to predict future trends. When that baby boom bulge moves into the 75-plus cohort, what happens to healthcare costs? You know the answer. An indentation, a narrower than expected bar, tells you something suppressed births or increased deaths at a specific time. An indentation in the young adult male cohort might indicate war casualties. A narrow bar in a particular birth cohort might reflect a famine, pandemic, or period of political instability when families chose not to have children. China's population pyramid shows a classic distortion from the one-child policy, which dramatically narrowed younger cohorts from 1980 onward. Migration also distorts pyramids in predictable ways. A receiving country, a classic destination for labor migrants, will show a bulge of young adult males because labor migration is dominated by that demographic. The United Arab Emirates is a stunning example. Its pyramid has an extraordinary bulge of males aged 25 to 45, completely dwarfing the female bars because of the massive guest worker population. Ascending country will show the opposite indentation in that same cohort. Recognizing this is an MCQ favorite, so train yourself to see a lopsided young adult section and immediately think migration. Key calculations and the dependency ratio. You must be able to calculate and interpret the dependency ratio, which the College Board defines as the ratio of the dependent population, those too young or too old to work, typically under 15 and over 64, to the working age population ages 15 to 64. The formula is, take the number of people under 15 plus the number over 64, divide by the number of people aged 15 to 64, and multiply by 100. A ratio of 60 means there are 60 dependents for every 100 working-age adults. Expansive pyramids generate very high dependency ratios because of all those children. Constrictive pyramids generate high dependency ratios too, but driven by the elderly rather than the young, and this distinction matters enormously for the exam and for real-world policy. Common exam traps and FRQ scoring points. The most common wrong answer trap is confusing the shape of the pyramid with the stage of the DTM. Remember, a constrictive pyramid does not mean stage 2, it means stage 4 or 5. Another trap is misidentifying what a bulge means. Always ask yourself whether a wide bar represents a large birth cohort or the result of in-migration. On FRQs, the rubric almost always awards points for correctly identifying the pyramid type, connecting it to a DTM stage, and then explaining the consequences. So practice moving through that 3-step logic every time. This topic connects directly to Unit 2's discussions of the demographic transition model, natural increase rate, and migration theory, and it will resurface in Unit 7 when you examine how demographic change shapes economic development and urbanization patterns. With a strong grasp of population pyramids, you're ready to explore how all that demographic data gets translated into theories of population growth and the demographic transition model itself, which is exactly where we're headed next. 2.5 Population Dynamics: Births, Deaths, and Natural Increase. The engine beneath the population. Imagine a bathtub. Water flows in through the faucet, water drains out through the drain, and the level in the tub rises or falls depending on which force is stronger. That bathtub is your mental model for every country's population. Births are the faucet, deaths are the drain, and the difference between them, what geographers call natural increase, is whether the water level is rising or falling. Simple in concept, but on the AP exam, the details buried inside this model are where students win or lose points. Let's walk through all of it together. The core formulas you must know cold. The AP exam will absolutely test your ability to calculate and interpret these rates, so let's get precise. The crude birth rate, or CBR, is the number of live births per 1,000 people in a population in a given year. The formula is CBR equals number of live births divided by total population, 19 minus 9,000. Notice that word crude. It's crude because it uses the entire population as the denominator, including elderly men and young children who can't actually give birth. That's a deliberate imprecision built into the measure, and the exam sometimes asks you to identify this as a limitation. Similarly, the crude death rate, or CDR, is the number of deaths per 1,000 people per year. Formula: CDR equals number of deaths divided by Same logic, same limitation. It doesn't account for the age structure of the population at all. Now here's the big one: natural increase rate, or NIR, sometimes called the rate of natural increase, or RNI. NIR equals CBR minus CDR, and the result is typically expressed as a percentage rather than per thousand. So if a country has a CBR of 30 and a CDR of 10, your NIR is 20 per thousand, which you convert to 2.0%. That conversion trips students up constantly. Divide by 10 to go from per thousand to percent. Write that in the margin of your scratch paper on exam day. Notice also what NAR does not include: migration. NAR measures only the natural component of population change. Total population change also requires factoring in net migration, but that's a separate calculation on the AP exam. If a question asks specifically about natural increase, migration is irrelevant, and including it in your answer is a trap that costs points. The doubling time concept. The exam loves to connect NIR to doubling time, how long it takes a population to double at its current growth rate. The rule of thumb formula is doubling time equals 70 divided by NIR expressed as a percent. This is called the rule of 70, and it's a quick mental math shortcut. A country growing at 2% annually doubles in roughly 35 years. A country growing at 1% doubles in about 70 years. A country growing at 0.1%, like many in Europe, doubles in 700 years, effectively a near-static population. The rule of 70 only works reliably at modest growth rates, and the AP exam won't ask you to calculate doubling time for extreme values, but knowing its logic matters. Connecting to the demographic transition model. Here's where this section plugs into the most important diagram in all of AP Human Geography, the demographic transition model, or DTM. You need to be able to sketch this graph from memory. Draw two axes, time on the horizontal, rates on the vertical. Draw two curves across the graph, a CBR curve, birth rate, and a CDR curve, death rate. The gap between those two curves at any point in time is the NIR, where the gap is largest. Population is growing fastest. In stage 1, both rates are high and roughly equal, so NAR is near zero, a pre-industrial society. In stage 2, the CDR drops sharply, thanks to improved sanitation, medicine, and food supply, while the CBR stays high. That widening gap creates rapid population growth. This is where many sub-Saharan African countries sit today. In stage 3, the CBR begins falling as urbanization rises, women gain education and economic opportunity, and family planning becomes accessible. The gap narrows. In stage 4, both rates are low and roughly equal again, so NIR approaches zero. This describes most of Western Europe. In stage 5, the CBR actually dips below the CDR, giving you a negative NIR, meaning the population naturally shrinks. Japan and Germany are your go-to examples here. A common MCQ trap. Students see that a country has a low CDR and assume it must be wealthy and developed, but actually, a young population in stage 2 can have a very low CDR simply because most people are young and not dying yet, not because healthcare is excellent. This is why age structure matters so much, and it's why the crude death rate is, well, crude. Total fertility rate, the finer measure. Because CBR has that age structure limitation, geographers also use total fertility rate, or TFR, which measures the average number of children a woman would have over her entire reproductive lifetime if current age-specific birth rates held constant. TFR is more precise than CBR because it isolates the behavior of women of reproductive age. The magic number to memorize. A TFR of Diplo-2-1 is replacement-level fertility in developed countries, the point at which a population replaces itself without growing or shrinking. It's 2.1 rather than 2.0 because some children die before reaching reproductive age. In countries with higher infant and child mortality, replacement-level TFR is correspondingly higher, sometimes above 3. The AP exam may ask you to distinguish CBR from TFR. Know that TFR is the better predictor of long-term population trends, while CBR is easier to calculate but distorted by age distribution. Infant mortality rate and life expectancy. Two more measures round out this section. Infant mortality rate, or IMR, counts deaths of children under age 1 per 1,000 live births. It's one of the single best proxy indicators for a country's overall development level, healthcare quality, nutrition, access to clean water, and maternal education all converge in this one number. Countries with IMRs below 10, like Japan or Norway, are highly developed. Countries above 50 face significant development challenges. Life expectancy at birth is the average number of years a newborn can expect to live given current mortality conditions. Both IMR and life expectancy connect directly to Unit 7 on development when you start comparing HDI components. Putting it together for the FRQ on a free response question. If you're asked to explain why a country has a high NAR, don't just say more births than deaths. Explain the reasons. High TFR driven by limited women's education, young population structure, limited access to contraception, economic incentives for large families and agricultural societies, or persistent cultural norms favoring large families. The scoring rubric rewards cause and effect reasoning, not just label identification. Similarly, if asked to explain a declining NIR, connect it to urbanization, rising female literacy, improved access to family planning, or economic development shifting the cost-benefit calculus of childbearing. Understanding these dynamics, how birth rates and death rates interact to drive natural increase, sets you up perfectly for the next section, where you'll see how these same forces, combined with migration, reshape the age and sex structure of populations through population pyramids. 2.6. Calculating CBR, CDR, NIR, TFR, and IMR. The language of population change. All right, let's talk numbers, but not in a scary way. Think of demographic rates as the vital signs of a country. Just like a doctor checks your heart rate and temperature to understand how healthy you are, geographers use a specific set of rates to understand how a population is growing, shrinking, or transforming. The 5 rates you need to master for the AP exam are the crude birth rate, the crude death rate, the natural increase rate, the total fertility rate, and the infant mortality rate. Each one tells a different part of the story, and together they paint a full picture of where a country sits in its demographic journey. Crude birth rate, CBR. Let's start with the crude birth rate, or CBR. The formula is straightforward. CBR equals the number of live births in a year divided by the total mid-year population, multiplied by 1,000. So if a country of 10 million people records 200,000 births in a year, the CBR is 20, meaning 20 births per 1,000 people. That, per 1,000 framing is important. The AP exam will always expect you to express CBR this way, not as a percentage. The word crude here is a technical term, not an insult. It means the rate uses the entire population as its base, rather than a more refined subset. This is actually a subtle trap on the exam. The CBR doesn't account for age structure, so a country with lots of young women will naturally have a higher CBR than an aging country, even if individual women are having the same number of children. Keep that limitation in the back of your mind. It's why we also need the TFR, which we'll get to in a moment. Globally, CBRs tend to cluster between about 10 and 50, with Stage 1 and Stage 2 countries of the demographic transition model sitting near the high end, and Stage 4 and Stage 5 countries near the low end. Crude death rate, CDR. The crude death rate follows identical logic. CDR equals the number of deaths in a year divided by the total mid-year population, multiplied by 1,000. A country with 50,000 deaths in a population of 5 million has a CDR of 10. Like the CBR, it's expressed per 1,000 people, and like the CBR, it's crude because it uses the whole population regardless of age. Here's a classic MCQ trap you need to know cold. A highly developed country with an older population, think Japan or Germany, can actually have a higher CDR than a developing country, even though its healthcare system is vastly superior. Why? Because more of its people are elderly and naturally more likely to die. Don't conflate a high CDR with poor healthcare. The exam loves this reversal. Always connect CDR back to the age structure of the population, and connect both CBR and CDR to the appropriate stage of the demographic transition model. Natural increase rate, NIR. Now here's where it gets satisfying, because the natural increase rate is simply CBR minus CDR divided by 10, and that division by 10 converts the rate from per 1,000 to a percentage. So if a country has a CBR of 28 and a CDR of 8, its NIR is 28 minus 8 divided by 10, giving you 2%. That means the population is growing at 2% per year through natural processes alone. The word natural is critical on the FRQ. NIR only accounts for births and deaths, not migration. It does not equal the overall population growth rate unless net migration is zero. The AP exam absolutely tests this distinction, so make sure you never mix up NIR with total population growth rate. A positive NIR means a population is growing naturally. A negative NIR, common in Stage 5 countries like several Eastern European nations, means more people are dying than being born. This concept connects directly to Unit 2's discussion of population pyramids. A country with a negative NIR will show a population pyramid that's narrow at the base and wider in the middle and top, a shape sometimes called an inverted or constrictive pyramid. Total fertility rate, TFR. The total fertility rate is a more refined and powerful tool than the CBR. TFR represents the average number of children a woman would have during her entire reproductive lifetime, typically defined as ages 15 to 49, if current age-specific fertility rates held constant. It's not calculated from a single formula the way CBR and CDR are. Instead, it's derived by summing age-specific fertility rates across all reproductive age groups. For the AP exam, you won't be asked to compute TFR from raw data, but you absolutely must know its meaning, its benchmarks, and its implications. The magic number here is 2.1, which is the replacement level fertility rate for developed countries. At 2.1, a population exactly replaces itself. The 0.1 accounts for childhood mortality and a slight natural imbalance in birth sexes. In countries with higher child mortality, the replacement rate climbs closer to 3 or above. A TFR below 2.1 in a developed country signals long-term population decline without immigration, which is a major policy concern for countries like South Korea, where TFR has recently dipped below 1.0. A TFR well above 2.1, common in parts of sub-Saharan Africa where rates can exceed 5 or 6, signals rapid natural increase. The TFR is a far better indicator of a population's reproductive behavior than the CBR because it controls for age structure. This is a comparison the exam frequently asks you to make. Infant mortality rate, IMR. Finally, the infant mortality rate measures the number of deaths of children under age 1 per 1,000 live births in a given year. Notice the denominator is live births, not total population. That's a detail that trips people up. IMR is one of the most powerful single indicators of a country's overall development level because it captures the quality of healthcare, nutrition, sanitation, and maternal education all at once. Countries in Stage 4 and Stage 5 of the DTM tend to have IMRs in the single digits, while countries still in Stage 2 may have IMRs above 50 or even 100. The AP exam often uses IMR as a proxy for development in both multiple choice and free response questions, and you should feel comfortable explaining why a low IMR correlates with late-stage demographic transition. Connecting the 5 rates to the big picture. When you sit down for the AP exam and see a data table showing demographic statistics for several countries, your job is to read those 5 rates as a coherent story. High CBR, high CDR, low TFR relative to the CBR, meaning high child mortality is distorting things, and a high IMR, that's a Stage 2 country. Low CBR, low CDR approaching or exceeding the CBR, a TFR below 2.1, and a near zero IMR. Welcome to Stage 4 or Stage 5. The rates are not isolated facts to memorize, they're interlocking clues that reveal a country's position in the demographic transition model and its likely trajectory for urbanization, economic development, and migration pressure. With those 5 vital signs in hand, you're ready to take the next step and explore how populations actually move through space, because as you're about to see, migration adds the layer that NIR deliberately leaves out. 2.7. The Demographic Transition Model, DTM. All right, let's talk about one of the most important models in all of AP Human Geography, the Demographic Transition Model, or the DTM. If you understand this model deeply, and I mean really deeply, not just memorizing the stage names, you'll be able to answer a huge range of questions on both the multiple choice and the free response sections. So grab your coffee because we're going to walk through this carefully. What the DTM actually is, Think of the DTM as a story about how countries change over time as they develop economically. It describes the historical shift from high birth rates and high death rates, the kind of demographic reality you'd find in a medieval village, to low birth rates and low death rates, which is the reality of a modern industrialized country today. The model was developed in the mid-20th century based on the observed experience of Western European nations, and it has since been applied globally, with some important caveats we'll get to. Here's the core insight. Death rates and birth rates don't fall at the same time. Death rates fall first, usually because of improvements in medicine, sanitation, and food supply. Birth rates take much longer to decline because they're tied to cultural values, women's education, access to contraception, and economic incentives. That gap between falling death rates and still high birth rates is where population explosions happen. Keep that timing difference in your head. It's the engine that drives the whole model. Drawing and labeling the DTM graph. You absolutely must be able to draw this graph from memory because the AP exam can ask you to sketch or interpret it. Here's how to set it up. Your x-axis represents time, moving from left to right. Your y-axis represents rates, specifically birth rates and death rates per 1,000 people. You draw two curves. The death rate curve drops earlier and more steeply. The birth rate curve stays high for a while, then gradually declines. The space between those two curves, where birth rate is higher than death rate, represents natural increase, meaning population growth. When the two lines converge again at low levels, population growth levels off. The model is divided into 5 stages, though some textbooks present only 4. The College Board generally expects you to know 5. In Stage 1, both birth rates and death rates are high, roughly balanced, so population is relatively stable but low. Think pre-industrial societies, hunter-gatherers, medieval Europe. No country today is in Stage 1. In Stage 2, death rates begin to fall sharply, thanks to things like clean water, vaccines, and better food, but birth rates remain high. Population explodes. This is where sub-Saharan African countries and parts of South Asia have historically been, though many are moving out of it. Stage 3 sees birth rates beginning to fall as women gain more education and economic opportunities, urbanization increases, and children become a financial cost rather than a labor asset on the farm. Population still grows, but more slowly. Countries like India and Mexico have been examples here. In Stage 4, both rates are low and roughly equal again. Population stabilizes. Think of Western Europe, the United States, and Japan. Stage 5, which not all textbooks include but the College Board does recognize, is where birth rates actually fall below death rates, leading to natural decrease. Population shrinks without immigration. Countries like Germany, Italy, and Japan are now experiencing this. The natural increase rate formula. Here's the formula you need to know cold. Natural increase rate equals birth rate minus death rate divided by 10, expressed as a percentage. So if a country has a birth rate of 30 per 1,000 and a death rate of 10 per 1,000, you subtract to get 20, then divide by 10 to get a 2% natural increase rate annually. On the multiple choice, they'll give you the raw rates and expect you to calculate this. A Stage 2 country might have an error around 2 to 3%, while a Stage 4 country might be at 0.1 or 0.2%. The most common MCQ traps. Here's where students lose points. First, many students assume that a high birth rate means a country is overpopulated or poor, and while there's a correlation, the DTM is specifically about rates, not total population size. China, for instance, has a massive total population, but is in Stage 4 because its birth and death rates are both now low. Second, watch out for questions that ask which stage a country is in based on a graph. Stage 2 and Stage 3 both show population growth. The difference is that in Stage 2 birth rates are still very high and death rates have just begun to fall, while in Stage 3 birth rates are actively declining. If the birth rate curve is clearly sloping downward, you're looking at Stage 3. Third, don't confuse natural increase with total population change. A country in Stage 5 can still grow in total population through immigration. Net migration can offset or even reverse natural decrease. The DTM only captures natural change, not migration. Limitations and edge cases. The DTM was built on the Western European experience, which means it assumes a particular development pathway. Some countries have moved through the stages very rapidly, due to government policy. China's one-child policy, for example, artificially accelerated the decline of birth rates in a way the model doesn't predict. Other countries in sub-Saharan Africa have experienced falling death rates without the expected economic development, creating prolonged Stage 2 conditions. This is a common FRQ angle, asking you to evaluate a limitation of the model or apply it to a country that doesn't fit neatly. When you write about limitations, be specific. Say that the model doesn't account for government population policy, or that it doesn't predict the speed of transition, or that it was based on a Eurocentric development pattern. Connections to other units. The DTM connects beautifully to so many other parts of this course. In Unit 2, it links directly to population pyramids. Each DTM stage has a characteristic pyramid shape, from the wide base pyramid of Stage 2 to the more rectangular or inverted shape of Stage 4 and 5. It also connects to the epidemiological transition model, which explains why death rates fall in terms of changing disease patterns. In Unit 3, you'll connect it to rural to urban migration patterns that accompany Stage 3 transitions. In Unit 5, agricultural development and the Green Revolution are part of what pushed many countries into Stage 2 by reducing famine-related death rates. And in Unit 7, the DTM links to economic development indicators like GDP per capita and the Human Development Index, which tend to correlate with higher DTM stages. For FRQ responses, the College Board rewards you for naming the stage, describing the characteristics of both birth and death rates in that stage, explaining why those rates exist in that society, and connecting the stage to real-world outcomes like dependency ratios or labor force composition. A student who just says Stage 3 means the birth rate is falling will earn fewer points than one who explains that birth rates fall in Stage 3 because of urbanization, rising female literacy, and the shift from agricultural to industrial economies. As you've seen, the DTM is really a lens for understanding population change over time. And that lens will come back into focus when we start examining how and why people move in the first place, which brings us right to our next topic, migration. 2.8 The Epidemiological Transition Model. The big idea, how diseases change as societies develop. Imagine you're a doctor in 1800s London, and your waiting room is packed with patients dying of cholera, smallpox, and tuberculosis. Now fast forward to a modern hospital in Tokyo, where the waiting room looks completely different. Patients dealing with heart disease, cancer, and diabetes. That shift in what people die from as a country develops economically and socially is precisely what the epidemiological transition model, or ETM, captures. Think of it as the demographic transition model's medical twin, where the DTM tracks births and deaths. The ETM zooms in and asks, what exactly are people dying of and why? The model was developed by Abdel Amran in 1971, and the College Board absolutely expects you to know its stages, their characteristics, and how they connect to broader patterns of development. Let's walk through it. The 4, and sometimes 5 stages. Stage 1 is called the age of pestilence and famine. This corresponds directly to Stage 1 of the DTM. Pre-industrial societies with high birth rates and high death rates. Life expectancy hovers around 20 to 40 years. The dominant killers here are infectious and parasitic diseases, plague, cholera, smallpox, typhus, and famine-related illnesses. Death rates are high, but also wildly unpredictable. A plague epidemic can wipe out a third of a population, then recede. Think medieval Europe during the Black Death. The key phrase the AP loves, high, fluctuating death rates. Stage 2 is the age of receding pandemics. Death rates begin falling, not primarily because of medicine, and this is a critical detail for MCQs, but because of improved nutrition, sanitation, and public health infrastructure. Clean water systems, better sewage disposal, and more reliable food supplies mean infectious diseases start losing their stranglehold. Cholera epidemics become less frequent. Life expectancy climbs toward 50 years. This stage parallels DTM stages 2 and 3. Population growth accelerates because deaths are falling while births remain high. Sub-Saharan Africa today contains countries that are transitioning through this stage. Stage 3 is the age of degenerative and man-made diseases. Here's where the story gets interesting. Once infectious diseases are largely controlled, people live long enough to develop the chronic, slow-burning conditions associated with aging and modern lifestyles: cardiovascular disease, stroke, cancer, and diabetes. These are degenerative diseases they develop over decades, often linked to diet, sedentary behavior, and environmental exposure. Life expectancy now exceeds 70 years. The United States moved through this stage in the mid-20th century. This parallels DTM Stage 4, where both birth and death rates are low. Stage 4 is the age of delayed degenerative diseases. This is where many highly developed countries sit today, and it's the stage students most often forget exists. Medical technology, statins for cholesterol, bypass surgeries, chemotherapy, cancer screenings, doesn't eliminate chronic diseases but delays death from them. Someone has a heart attack at 55 and survives because of advanced cardiac care, living another 25 years. Life expectancy climbs above 75 to 80 years. The key distinction from Stage 3: the diseases are the same, but improved medical management pushes death further and further into old age. Stage 5 is a contested addition that some scholars have proposed, called the age of emerging and re-emerging infectious diseases. HIV/AIDS, drug-resistant tuberculosis, Ebola, COVID-19, these suggest that infectious disease never truly disappears. Developed countries may face new epidemic threats even after achieving Stage 4. The College Board has referenced this stage, so be aware it exists, but know that it's not as universally accepted as Stages 1 through 4. If an FRQ or MCQ mentions re-emerging infectious diseases in wealthy countries, Stage 5 is what they're pointing toward. Drawing and interpreting the model for the AP exam. You need to be able to visualize this model alongside the DTM. Picture two line graphs sharing an x-axis of time or development level. The DTM shows birth rate and death rate lines converging. The ETM, placed below, shows a stacked bar or area chart illustrating the composition of deaths shifting from infectious diseases, dominant in Stages 1 and 2, to chronic and degenerative diseases, dominant in Stages 3 and 4. If you're asked to sketch this, label the x-axis as stages of development, 1 through 4 or 5. Label the y-axis as causes of death, and show infectious diseases declining as a proportion while degenerative diseases rise. The visual story is a crossover. Around Stage 2 to 3, the two categories trade dominance. The most common MCQ traps. Here's where students consistently lose points. First, many students confuse why death rates fall in Stage 2. The wrong answer says improved medical technology and vaccines. The right answer emphasizes improved sanitation, nutrition, and public health infrastructure. Vaccines and antibiotics come later and contribute to Stage 3. Second, students conflate the ETM with the DTM itself. Remember, the DTM describes rates of birth and death. The ETM describes the causes of death. They're complementary models, not the same model. Third, watch out for questions about life expectancy. Stage 4 does not mean people stop dying from heart disease. It means they die later from it. Another trap: when a question describes a country where infectious disease deaths are rising again in an otherwise developed nation, think HIV/AIDS in the U.S. in the 1980s and 90s, or COVID-19, don't assume the country regressed to Stage 2. That's Stage 5 logic, re-emergence within an otherwise advanced epidemiological context. Connecting to other units. The ETM doesn't live in isolation on the AP exam. It connects directly to the DTM Unit 2, where epidemiological stage explains why death rates change. It connects to healthcare access and medical geography. Countries in Stage 1 or 2 lack the infrastructure for Stage 3 and 4 diseases because their healthcare systems are built around infectious disease treatment, not long-term chronic disease management. The ETM also appears in development discussions from Unit 7, since a country's epidemiological stage is a strong indicator of its HDI and overall quality of life. When the AP asks you to explain disparities in life expectancy between high-income and low-income countries, the ETM is part of your toolkit. Finally, migration connects here too, when people migrate from stage 2 countries to stage 3 or 4 countries. They sometimes bring higher rates of infectious disease exposure, and they may also adopt the chronic disease risks of their new environment over time, a phenomenon called the immigrant health paradox that occasionally appears in stimulus-based FRQs. Understanding how humanity's relationship with disease has evolved over time isn't just exam content, it's one of the most profound stories in human history, and it sets the stage perfectly for our next topic, which examines how all of these population pressures and patterns shape the movement of people across the globe. 2.9 Malthusian Theory and Neo-Malthusian Perspectives. The setup, a clergyman's grim prediction. Let's travel back to 1798 England. A clergyman and economist named Thomas Robert Malthus sits down and writes what will become one of the most debated essays in the history of social science. His central argument is elegant, terrifying, and, depending on who you ask, either completely wrong or more relevant than ever. Here's the core idea: human population grows geometrically, doubling over and over like compound interest, while food production grows only arithmetically, adding a fixed amount each year. Picture it this way: if you start with a penny and double it every day, after 30 days you have over $5 million. Now imagine food production just adds a penny per day. You can see where this ends badly. Malthus used specific language the College Board expects you to reproduce precisely. Geometric, or exponential growth follows a pattern like 1, 2, 4, 8, 16. Each step multiplies the last. Arithmetic, or linear growth, looks like 1, 2, 3, 4, 5, always adding the same fixed amount. On the AP exam, if you see a question asking what kind of growth Malthus assigned to population versus food supply, your answer must be geometric for population, arithmetic for food. Swapping those two is one of the most common wrong answers on multiple choice. Don't fall for it. Checks, preventive and positive. Now, Malthus wasn't just predicting doom and walking away. He identified mechanisms, he called them checks, that would prevent population from permanently outstripping food supply. He divided these into 2 categories, and you need both. Preventive checks are the ones people choose to do before disaster strikes. They delay or reduce reproduction, things like postponing marriage, celibacy, or what Malthus called moral restraint. These are anticipatory. Positive checks, on the other hand, are the brutal ones nature or society imposes after the fact: famine, disease, and war. Notice the ironic language here. Positive doesn't mean good. It means they actively increase the death rate to bring population back in line with resources. When population overshoots food supply, positive checks kick in and bring the numbers back down. Malthus called this ceiling the Malthusian ceiling, or the point at which resource scarcity triggers catastrophic mortality. On an FRQ. If you're asked to explain Malthusian theory, you earn points by naming both types of checks, providing an example of each, and connecting them to the relationship between population and food supply. A student who only writes famine and disease and skips preventive checks will leave points on the table. Drawing the Malthusian graph. You absolutely need to be able to describe and, if asked, sketch the classic Malthusian diagram. Draw 2 lines starting from the same origin point. The population line curves upward steeply like an exponential function. The food supply line climbs at a gentler, straight-line angle. Where the population line surpasses the food supply line, you've hit the Malthusian crisis point. At that intersection and beyond, positive checks bring population back down. Imagine the population line hitting a ceiling, and either leveling off or dropping. Label your axes. Vertical axis is population, food supply, quantity. Horizontal axis is time. Label the 2 lines, mark the crisis point, and if you're feeling thorough, draw a small arrow showing population declining after the check kicks in. That diagram tells the whole story. Enter the Neo-Malthusians. Here's where it gets interesting for the modern world. Malthus didn't anticipate the Green Revolution, fertilizers, genetic modification, or global food trade networks. Agricultural productivity exploded in ways he simply couldn't foresee, and critics correctly pointed out that food production has repeatedly outpaced his prediction. But a group of thinkers in the 20th century said, wait, Malthus had the right framework, just the wrong resource. These are the Neo-Malthusians, and their update to his theory is critical for the AP exam. Neo-Malthusians argue that the real constraint isn't just food, it's the full range of Earth's resources and environmental carrying capacity. Think oil, fresh water, arable land, clean air, biodiversity. The logic is the same. Exponential population growth will eventually run up against finite limits, triggering a crisis. Paul Ehrlich's 1968 book, The Population Bomb, is the classic Neo-Malthusian text. The Club of Rome's 1972 report, The Limits to Growth, used computer modeling to project resource depletion. Both argued that without dramatic intervention, either slowing population growth or radically changing consumption patterns, collapse was inevitable. The key distinction the AP exam loves to test is this. Malthus focused specifically on food supply. Neo-Malthusians expand the concern to all natural resources and environmental limits. If a question asks what separates Neo-Malthusians from original Malthusian theory, that's your answer. Common traps and edge cases. Watch out for a few sneaky MCQ traps. First, don't confuse Neo-Malthusianism with antinatalist policy. Neo-Malthusians analyze a problem. Specific government policies, like China's former one-child policy, are applications or responses to that concern. They aren't Neo-Malthusianism itself. Second, Malthus was writing in the context of 18th century England. He was not a demographer describing all societies equally. When the AP gives you a country that has dramatically increased agricultural output, that's a scenario where critics of Malthus would say his model failed, not succeeded. Third, remember that Malthus has been both supported and contradicted by history. The exam may ask you to evaluate evidence for and against his predictions, so stay balanced. Connections across units. This topic threads beautifully through the rest of the course. In Unit 2, Malthusian theory connects directly to the demographic transition model. The DTM's Stage 2 population explosion is exactly what Malthus feared, while Stages 3 and 4, falling birth rates, represent a kind of voluntary preventive check society figured out on its own. In Unit 5, Agriculture. The Green Revolution is the single most important historical counter-argument to Malthusian predictions, so expect questions linking those two topics. Neo-Malthusian thought also surfaces in Unit 5 discussions of sustainability, and Unit 7, Industrial and Economic Development, when examining resource consumption patterns in developing versus developed countries. Carrying capacity, a concept from environmental science, is the Neo-Malthusian framework applied to geography, and it appears frequently in FRQ prompt. When you see a question about population policy, resource depletion, or agricultural innovation, ask yourself, is this evidence for Malthus, against Malthus, or a Neo-Malthusian extension? That mental checklist will keep you oriented. As we move forward, you'll see how governments actually respond to population pressures through pronatalist and antinatalist policies, which brings us directly to our next topic on population policies and demographic intervention. 2.10 Population Policies, Pronatalist and Antinatalist. What are population policies, and why do governments care? Imagine you're running a small country. Look around and suddenly you realize you have a problem. Maybe there are too many people and not enough food, jobs, or water. Or maybe the opposite, your population is shrinking so fast that there won't be enough young workers to support an aging society in 30 years. Either way, you're not just going to sit back and watch, you're going to do something. That's exactly what population policies are. Deliberate governmental strategies designed to influence the size, growth rate, or composition of a country's population. For the AP exam, you need to understand two major categories, pronatalist and antinatalist policies, and you need to be able to connect them to the demographic context that makes each one logical. Pronatalist policies. When governments want more babies, Pro-natalist policies are efforts by governments to increase the birth rate. The prefix pro means for, and natalist comes from the Latin for birth, so think of it as being pro-birth. Countries adopt these policies when they're facing population decline, an aging population, or a shrinking labor force. This is a classic late stage 4 or stage 5 demographic transition scenario, and that connection is critical for your exam. The go-to example here is France, and it's one you should absolutely have memorized. France has offered generous financial incentives for decades, paid parental leave, subsidized childcare, monthly stipends for each additional child, and even baby bonuses paid directly to parents. The logic is straightforward: lower the economic cost of having children, and more people will have them. Sweden, Germany, and Japan have implemented similar strategies. Japan is particularly striking because its total fertility rate has hovered around 1.2 to 1.3 for years, well below the replacement level of 2.1, and the country is facing a genuine demographic crisis. In response, the Japanese government has expanded parental leave, built more child care centers, and even run national campaigns encouraging people to have more children. Here's a useful analogy. Think of pro-natalist policy as a store running a sale. The government is essentially discounting the cost of parenthood through subsidies, tax breaks, and social support, hoping that lower prices will increase demand. But just like not every sale leads to a buying frenzy, pro-natalist policies don't always dramatically spike the birth rate. This is an important edge case for MCQs. Pro-natalist policies are not guaranteed to raise the TFR significantly, especially in highly urbanized, economically developed countries where social and cultural norms around family size are already well established. Antinatalist policies, when governments want fewer babies. Antinatalist policies work in the opposite direction, governments trying to decrease the birth rate, typically in response to rapid population growth, resource strain, or concerns about development. These policies are most common in countries in Stage 2 or early Stage 3 of the demographic transition, where death rates have fallen but birth rates remain high. The example that dominates every AP Human Geography course is China's one-child policy, implemented in 1980 and officially ended in 2015. This was one of the most aggressive anti-natalist interventions in history. Families in urban areas were largely restricted to one child, enforced through a combination of financial penalties, social pressure, and in some documented cases, coercive measures. The policy dramatically reduced China's total fertility rate and is credited with slowing population growth. But it also created significant unintended consequences: a heavily skewed sex ratio because of a cultural preference for male children, an aging population, and a shrinking labor force. China's shift to a two-child policy in 2015 and then a three-child policy in 2021 reflects how quickly anti-natalist logic can flip to pro-natalist logic as demographic conditions change. That policy reversal is a perfect example for FRQ responses about how policies adapt to shifting demographic realities. India offers another rich case study. Rather than a single mandatory policy, India pursued a series of family planning programs beginning in the 1950s, emphasizing voluntary contraception access, education, and incentives for smaller families. Some Indian states went further with sterilization programs in the 1970s that became deeply controversial. The takeaway for the exam: anti-natalist policies exist on a spectrum from gentle education and access campaigns to coercive mandates, and the AP exam may ask you to evaluate the ethical dimensions or effectiveness of these approaches. Connecting to other units and key concepts. This topic is deeply woven into the rest of Unit 2, and you should be thinking about those connections constantly. Population policies are a response to the demographic transition model. Knowing what stage a country is in tells you which type of policy it's likely to need. A country in Stage 2 with a booming young population and strained resources is a candidate for anti-natalist approaches. A country in Stage 4 with a low TFR and a graying population is a candidate for pro-natalist measures. You should also connect this topic to the epidemiological transition model, because shifts in disease burden and life expectancy are part of what drives governments to act. Beyond Unit 2, population policies connect to Unit 7, industrial and economic development, because labor force size directly affects economic productivity, and to gender equity discussions that appear across multiple units. Antinatalist policies often involve expanding women's access to education and healthcare, and geographers note that female education level is one of the strongest predictors of falling fertility rates anywhere in the world. That's a point that frequently appears in FRQ scoring rubrics. Common traps and exam tips. One of the most common MCQ traps is confusing immigration with antinatalist policy. If a country's population is declining, it might be because people are leaving, not because of any birth control policy. Always check whether the question is asking about birth rates specifically or overall population change. Another trap. Students often assume that antinatalist policies are always coercive and pro-natalist policies are always voluntary. In reality, both can involve incentives or mandates. The key distinction is the direction they push birth rates, not necessarily the method. For FRQs, when you're asked to explain a population policy, always do 3 things. Name the policy or country, explain the demographic problem it was responding to, and describe at least one specific mechanism or program used. Vague answers like, the government tried to lower the birth rate, won't earn full points. Specificity is everything. Transition. Now that you understand how governments actively shape their populations through pro-natalist and antinatalist policies, you're ready to zoom out and examine the patterns that result when people don't just stay when they pick up and move entirely. Which brings us into the rich and complex world of migration theory and patterns. 2.11 Women's status, education, and fertility rates. The core relationship, why education changes everything. Let's start with what might be the single most powerful demographic insight you'll carry into the AP exam. The education of women is the strongest predictor of fertility rates in any given society. Not wealth, not religion, not government policy, though all of those matter, but education, specifically the education of women. Think of it like a master key. When you raise women's access to education, you unlock changes in nearly every other demographic variable at once. Fertility rates fall, infant mortality drops, child health improves, and economic development accelerates. College Board loves this topic precisely because it ties together so many threads from Unit 2, and it shows up in both MCQ and FRQ formats year after year. So here's the core relationship you need to internalize. As women's educational attainment increases, total fertility rates, TFR, decrease. This is an inverse relationship, and you should be able to describe it, graph it, and explain the mechanisms behind it. The graph you need to picture is a scatterplot with TFR on the y-axis and average years of female schooling on the x-axis. As you move right along the x-axis, meaning more years of schooling, the data points cluster lower and lower on the y-axis. Countries like Niger and Mali, where female secondary school enrollment is low, consistently show TFRs of 6, 7, even 8. Countries like South Korea or Germany, where women's educational attainment matches or exceeds men's, show TFRs at or below replacement level, around 2.1 or lower. That 2.1 figure is your replacement level TFR. Burn it into your memory. Mechanisms. How does education actually lower fertility? This is where the AP exam goes deeper than simple memorization. You need to understand why this relationship exists, because FRQ prompts will often ask you to explain the mechanism, not just state the trend. When girls stay in school, several things happen simultaneously. First, the age of marriage rises. A girl enrolled in secondary school is not getting married at 14 or 15, she's in class. Later marriage compresses the fertile window, meaning fewer years during which pregnancy is biologically possible within a marriage. Think of it as shrinking the runway. Second, educated women gain economic agency. When a woman can earn income, she has bargaining power within the household. She can choose to delay or space pregnancies in ways that women without economic independence often cannot. Third, education raises awareness of and access to contraception. Educated women are more likely to know about family planning options and more likely to have the social standing to use them. Fourth, there's what demographers call the opportunity cost of child-rearing. When a woman has career prospects, each child represents not just an expense, but foregone income, and that calculus changes decision-making at the household level. Women's status beyond education, the broader picture. College Board also expects you to understand women's status as a broader concept that includes employment, political representation, legal rights, and social norms, not just years of schooling. The Gender Inequality Index, GII, produced by the United Nations, is the key metric here. It measures inequality across 3 dimensions: reproductive health, maternal mortality ratio and adolescent birth rate, empowerment, share of parliamentary seats and population with at least some secondary education, broken down by gender, and labor market participation, female and male labor force participation rates. Countries with high GII scores, meaning greater inequality, tend to have higher fertility rates and slower demographic transitions. Countries with low GII scores tend to cluster in the later stages of the demographic transition model. Speaking of the DTM, and this is a critical connection to keep in your back pocket, women's status and education are among the core drivers of the transition from Stage 2 to Stage 3 and ultimately into Stage 4. In Stage 2, birth rates are high partly because women have limited access to education and economic opportunity. As women's status rises, countries move into Stage 3 where birth rates begin falling. This is not coincidental. It is causal. The AP exam will often ask you to connect these dots explicitly, so practice saying, improvements in women's education and status contribute to the decline in crude birth rates characteristic of the Stage 2 to Stage 3 transition. Common MCQ traps and FRQ pitfalls. Here's where students lose points, and I want you to walk into that exam room forewarned. The most common trap is confusing correlation with causation and then being imprecise in your explanation. The exam is not just asking you to say more education equals fewer babies. It wants you to articulate the mechanisms: delayed marriage, increased opportunity cost, greater access to contraception, enhanced agency. Be specific. Another trap involves overgeneralizing religious or cultural influence. Students sometimes assume religion is the primary driver of high fertility, but the data don't fully support that as an independent variable. Countries within the same religious tradition show wildly different TFRs depending on women's educational attainment. Iran, for example, dropped its TFR dramatically in the 1990s and 2000s while remaining an Islamic republic, largely because female literacy and enrollment in higher education rose steeply. Be careful not to let a simple narrative override what the data actually show on FRQs. Watch for prompts that give you a country's demographic data and ask you to predict or explain its position on the DTM, or to compare 2 countries. If you see that country A has a low female literacy rate and country B has high female university enrollment, you should immediately connect that to expected TFR differences and stage of demographic transition. Rubrics award points for this kind of explicit geographic reasoning, not just listing facts, but connecting them. Also be alert to the edge case of sub-replacement fertility in highly educated societies. When TFR falls below 2.1, you're looking at Stage 4 or Stage 5 of the DTM, population aging, and potential population decline. Japan, South Korea, and many European nations face this reality. The AP exam occasionally tests whether you understand that the relationship between education and fertility doesn't stop at replacement level. It can push societies into demographic challenges from the other direction. Connections across the course. This topic doesn't live in a silo. It connects forward to Unit 7, where you'll examine development indicators and the role of gender equity in economic growth. It connects to the discussion of population pyramids. Countries with high female education and low TFR produce narrow-base, top-heavy pyramids characteristic of aging populations. It ties to migration patterns, because when women in developing countries gain education and face limited local opportunities, they may migrate, contributing to brain drain, and it connects to the concept of the epidemiological transition, which runs alongside the DTM and is similarly driven by improvements in women's health access and status. As you move into the next section, you'll begin exploring how migration itself reshapes population patterns across space, And you'll see echoes of everything we just discussed, because migrants carry demographic behaviors, including those shaped by women's status across borders with them. 2.12 Aging populations and dependency ratios. What's actually going on here? Imagine your household has 5 people living in it. 3 of them go to work every day and bring home paychecks. The other 2, let's say a toddler and an elderly grandparent, depend on those 3 workers for food, healthcare, and everything else. Now picture what happens if 2 of your workers retire and nobody new moves in. Suddenly, you've got 1 person supporting 4 dependents. That's exhausting, and it's expensive. That scenario, scaled up to the size of countries, is exactly what demographers mean when they talk about aging populations and dependency ratios, and it's one of the most consequential geographic challenges of the 21st century. The dependency ratio, the formula, you must know. The total dependency ratio is the cornerstone calculation for this topic, and you need to be able to use it confidently on both the MCQ and FRQ sections. Here's the formula. College Board expects you to know total dependency ratio equals population age 0 to 14 plus population age 65 and over, but population aged 15 to 64 times 100. The numerator captures your 2 dependent groups, children and the elderly, and the denominator is your working age population. The people presumed to be economically productive. Multiplying by 100 expresses the result as the number of dependents per 100 working age people. So if a country has a dependency ratio of 60, that means for every 100 workers, there are 60 dependents to support. A ratio of 100 means a perfect 1-to-1 split. Economically, that's a strained system. From this formula, you can also calculate 2 subratios. The youth dependency ratio uses only the 0 to 14 population in the numerator, and the elderly dependency ratio uses only the 65 and over population. This distinction matters enormously on the exam. A developing country like Niger might have a very high total dependency ratio driven almost entirely by its youth dependency. It has a youthful population with high birth rates. Japan, by contrast, has a high total dependency ratio driven by its elderly dependency. Birth rates have fallen, people are living longer, and the workforce is shrinking relative to retirees. Same formula, completely different geographic story. The population pyramid, your visual toolkit. You absolutely must be able to draw, label, and interpret a population pyramid for this topic. A population pyramid is a back-to-back horizontal bar chart with males on the left, females on the right, and age cohorts stacked from youngest at the bottom to oldest at the top. The x-axis shows either raw population numbers or percentages of the total population. The y-axis shows age groups, typically in 5-year increments. For an aging population, the pyramid stops looking like a triangle and starts looking like a column or even an inverted triangle, what geographers sometimes call a coffin shape. The base is narrow because birth rates are low, and the middle and upper sections are thick because large cohorts are moving into and through retirement age. Japan and Germany are your go-to examples here. When you see a pyramid like this on the exam, your brain should immediately fire off several connected ideas: low total fertility rate, low natural increase, high life expectancy, high elderly dependency ratio, and likely a stage 4 or stage 5 country on the demographic transition model. That connection to the demographic transition model is crucial for the FRQ. Stage 4 countries have both low birth rates and low death rates, producing a slow natural increase and an aging population. Stage 5, which is contested but increasingly recognized, involves birth rates falling below death rates, leading to natural population decline. Think Germany before immigration offsets it. Understanding where a country sits on the DTM tells you almost everything about what its dependency ratio looks like and why. What aging populations actually mean for societies? An aging population creates what economists call a demographic burden, and this is where the concept becomes rich with real-world application. The most pressing challenge is pension and healthcare costs. When a country's elderly dependency ratio rises, fewer working-age taxpayers are funding social security systems, public health programs, and elder care facilities designed for a much larger senior population. Japan is perhaps the world's most dramatic example. It has the world's oldest population, with nearly 30% of its people over age 65, and the country is actively paying young families to have children while simultaneously encouraging immigration, which is historically unusual for Japan. Here's a common MCQ trap you need to watch for. The exam may describe a country with a declining total population and ask you to infer the dependency ratio. Students often assume a shrinking population means a lower dependency ratio because there are fewer people overall. Wrong. A shrinking population often means birth rates have collapsed, so the youth cohort is tiny, the working age cohort is aging out, and the elderly cohort is proportionally massive. The dependency ratio can actually be rising even as the total population falls. Don't let raw population size mislead you. The demographic dividend and its window. On the flip side, when a country moves through the demographic transition and its large youth bulge enters the workforce before the elderly population becomes large, you get what demographers call the demographic dividend, a temporary sweet spot where the working age population is proportionally huge